In today's lesson, we are going to be looking at function notation. So again, continuing with this theme of characteristics of a function and what is a function, we're looking at what we call function notation. So it's a way to represent functions. So just a little bit of review. We want to take a look at this relation, and we want to state the domain and range. So again, remember, domain is referring to the x and y value, or the x values. So we did mention we can think of it as bringing like a trash compactor, right? So it's kind of coming in from either side, right? And basically, where do we touch our function or our relation? We are going to have the same general format. X is any real number because this is a graph. So we're going to have this format. X is any real number such that, and then we have basically our format to fill in. Right, so the low end, if I bring my kind of one end in on the left, okay, we have kind of a line coming across here. So that lowest value is at, it looks like, -7. So that means the lowest x can be is -7. And if I come in from the right side, we touch our relation here. So this means that our highest possible value is +7. So our domain is going to look something like this. X is any real number such that x is greater than or equal to -7, but less than or equal to +7. For range, it's going to be exactly the same thing, except we use y instead of x. So y is any real number such that, and then we have our general format. And for y, because y is looking at the vertical values, up and down, we are going to come up from the bottom and we hit a value, right? We hit our relation. So the lowest value there looks at about, we'll say -2.5, just for sake of argument, just so we don't get too nitpicky. So -2.5 is our lowest value. And then if we come down from the top and we hit our relation, we see we hit it right just below that line. So probably a little bit further down, right about there. And that is 3. So that means that our range is y is any real number given that or such that it is y is greater than or equal to -2.5, but less than or equal to 3. So again, that's the domain and the range for this relation. B now asks, is it a function? And from the lines we drew to find the domain, we probably guess, or not guess, but we should probably be able to tell that no, it is not. So no, it is not a function, right? And we can say that it fails the vertical line test. So it's not a function, it fails the vertical line test. Right? If you draw a vertical line somewhere along this relation, it's going to touch more than once. Continue with the review. What determines if a relation is a function or not? You could say the vertical line test, or you could say more than one y value for an x value, or for a given x value, right? Because the idea is we don't want to have more than one y value for a given x value. How does the vertical line test help us determine if a relation is a function? Basically, if it passes, it's a function. If it fails, it's not a function. And we could say that the reason that it fails, one, it fails the test, but then there's more than one y value. right? So it goes back to that definition of what a function is. What is domain? Right, so we did look at domain in the previous lesson. Domain refers to all the possible x values. So domain refers to all the possible x values, and range refers to all the possible y values. So domain, all the possible x values. Range, all the possible y values. Now we're going to get into function notation. So again, that was kind of a review of some of the characteristics of a function that we've looked at. Now we're going to get into function notation. So for function notation, we'll kind of have like a brief little intro. The shape of the Humber River pedestrian bridge in Toronto can be approximated by the equation h at x is equal to negative 1 over 144 x squared plus 5 over 6x. Right? H is the distance, or H is the height, in meters above the water, and x is the distance you have walked from one end as you cross it in meters. And the bridge is 138 meters long. So this equation up here is written using function notation. Right? So the key parts of function notation, everything in that equation looks pretty similar to equations we've dealt with before, but the key thing is this portion here. That's the function notation. So that small little bit there, that is the function notation. Let me just write this a little bit neater. Function notation. So that is the that portion, that h bracket x bracket is the function notation. Now it's commonly seen as f at x, so this is what we commonly see it as. And there's different ways we could describe this. We could say f at x, or we could say f of x. Two different ways we could represent or pronounce it. We could say f at x or f of x. And basically what that notation does, it represents the value of the dependent variable for a given value of the independent variable. Remember, dependent is referring to y, independent is referring to x. Basically, it's saying it's going to give us a y value for a given x value. Now, when we use function notation, the y and f at x are interchangeable. So we could rewrite, say, an equation or a function, say, for example, y equals mx plus b. I can rewrite that in function notation as f at x is equal to mx plus b. It's essentially the same thing. It's still representing our function. It's still representing the y value or the dependent variable. Right? So it's just rewriting it in a different way, because we can use that to kind of write out questions or ask questions or write out or simplify some of our scenario or sentences. Okay? And we can use x bracket f at x to represent a solution of f at x. So sometimes we might have a coordinate or a point for a function, an x and a y, right? We could just say x and f at x instead. Right? So again, it's just different notation that you may come across if we're dealing with functions. Right? And if we look at kind of a function machine, quote unquote, right? We input an x value, our function does some operations to it, and it outputs f at x, or the function at an x value, right? So at this x value, or given this x value, this is what our function is. So let's just look at a basic example. So when given a function f at x and asked to evaluate f at 4, right? Not fat 4, it's f at 4, right? So this is basically saying what is the value of our function when x is 4. And it says substitute 2. We don't mean 2. That's a typo there. We want to substitute in 4. Right? So given a function f at x and asked to evaluate f at 4, we substitute 4 into the equation for x. Because this value here, whatever is in the brackets, that is just our x value. Right? So that is telling us what our x value is going to be. So we have our function. It is f at x is equal to 2x squared plus 5x plus 1. We are going to evaluate that for f at 4 equals 2. And again, we're just going to replace all the x values with 4. So 2 times 4 squared plus 5 times 4 plus 1. F at 4 is equal to 16 times 2, 32, plus 20 plus 1. F at 4 is equal to 53. So I don't need to write anything further, right? I can just leave it at that at the end. So it's the function when x is 4, or f at 4, is equal to 53. So let's go through some practice with using the function notation. Right? So we're going to want to basically, for the following functions, determine f at 2, f at negative 5, and f at a half. Right, so all we're going to do is just basically plug in different values for x and calculate. So f at 2 is going to equal 2 times 2 minus 4. We get 4 minus 4, or 0. So that means f at 2 is equal to 0. Next one, f at negative 5 is equal to 2 times negative 5 minus 4. F at negative 5 is negative 10 minus 4, or f at negative 5 is equal to negative 14. Then our last one, f at a half is equal to 2 times a half minus 4. F at a half is equal to 1 minus 4, or negative 3. So again, all we're doing is just plugging in values or x values into our function and calculating. The only difference is we're given those values in function notation rather than just saying solve the following equation when x equals this, or substitute x into this equation and solve. We could just say determine f at 2. I'm going to try it with another equation. So again, or another function. So again, going to do the exact same thing. We're going to use f at 2, f at negative 5, and f at a half. We have a different function now, though, so it's going to be a different equation that we substitute in. So 3 times 2 squared minus 2 plus 7. So it's going to go into every x value that we see. So f at 2 is equal to 3 times 4, which is 12, minus 2 plus 7. So f at 2 is equal to 17. Next one, again, plug in negative 5. So 3 times negative 5 squared minus negative 5 plus 7. Let me just move all this down just to make sure we have enough room. So 3 times 25 is 75 plus 5 plus 7. F at negative 5 is equal to 87. And then our last one, we're plugging in a half. So we have 3 times a half squared minus a half plus 7. So we have 3 times a quarter, which is 3/4. 3 over 4 minus 1 over 2 plus 7. 3/4 minus a half is a quarter. So 1 over 4 plus 7. So F at a half is equal to 7.25. If I did my mental math correct, which there's always a chance that I did not. Lastly, f at x is equal to 87. So this one is a little bit different because if we go and try to plug in x is 2 into our function, we can't, right? Which just means that when x is 2, the function is equal to 87, right? Or when x is 2, the y value is 87. That's essentially what that is saying. And if we do the same thing with f at negative 5 equals 87, there's nothing we need to do. So the function, when x is negative 5, is 87. So there's the point negative 5, 87. And same thing for the last one. When f is a half, the function is equal to 87, or we have the point 1/2 and 87 existing on our function. So again, there's some different ways to use the function notation, just basically what it means if you do come across it. Now, we can also use that same idea when we're dealing with a graph. So the shape of the Humber River pedestrian bridge in Toronto can be modeled by the graph below. We want to determine f at 60, f at 20, and f at 120. So we have to remember this function notation just basically means f at x, or the function at when x is a certain value. So what is the value when x is 60? So essentially when we have a graph, all we have to do is go over, find our x value, in this case 60, go up until we hit our graph, and we find out what the y value is. So this looks like it's 25. So when f is 60, or when x is 60, the function is equal to 25. So f at 60 equals 25. For 20, f at 20, we can do the same thing. Go over to 20 and go up until we hit our function, or down, depending on what it happens to be. And we get our value. So that looks like it is 14. So f at 20 is 14, or when the x value is 20, the function is equal to 14. And then our last one, f at 20, or 120. So I go all the way over my x values to 120, and we see that it is equal to 0. So f at 120 is equal to 0. One last example, just looking at the relation and a different scenario. So the relationship between the selling price of a sleeping bag S dollars and the revenue at that selling price R at S is represented by the function R at S is equal to negative 10 S squared plus 1500 S. We want to determine the revenue when the sleeping bag costs $55. So essentially what we're doing is we're looking for R at 55. That's what this last portion at the end here. That is basically saying when is, or what does the function equal when S is 55. So all we have to do, S at 50, or R at 55 is going to equal negative 10 times 55. Oops. Terrible writing. negative 10 times 55 squared plus 1500 times 55. We're going to go through and calculate this now. Right? You can do it all in one step if you're comfortable with your calculator, or do it in multiple steps. So first we have negative 30,250 plus 82,500. We then calculate those together. We can do minus, or we get 52,250. So the revenue when S is 55 is $52,250, or R at 55 is equal to 52,250. Determine and explain the meaning of R at 85. So I can determine that first. R at 85 just basically again means I'm replacing the S value in our function with 85. Negative 10 times 85 squared plus 1,500 times 85. Just going through and doing these calculations. We get negative 72,250 plus 127,500, and then combine these two together, we end up with $55,250. So what does this mean? Therefore, if the sleeping bags cost $85, the revenue is $55,250. Last example, C, explain the meaning of 60 and 54,000. So again, just what does this mean in the context? Right? If we think of X and f at X, or X and Y, we can think of this as, again, when the bags cost $60, the revenue is $54,000. Right? So it's just basically, what does that point mean in the context of the situation? So the main thing from this lesson is just understanding what does function notation look like and what does it actually mean and how we can use it. Right? So again, it doesn't mean anything too tricky. It's just a different way of writing things, different way of introducing information, or different ways of presenting how a function or the equation of a function can look.